Making pretty pictures, free body diagrams, and the net force, not to be confused with fire-breathing dragons. This is our second unit in dynamics. I'm going to break it up actually over 2 screen artists, so I'm going to go a little bit slower because there's a lot of stuff in this particular screen art. So, a free body diagram is just simply a vector diagram. It shows all the forces acting on an object. So this spherical blue ball here, for example, is motionless. It's in equilibrium. What are the forces acting on it? Well, the force acting down is the weight, and the force acting up is the normal force. Notice that the forces are drawn as vectors. They have magnitude, the length of the arrow, arrowheads indicating their direction, and they must be properly labeled when you're drawing a free body diagram. So, when the net force is 0, we say the object is in equilibrium. It's not moving, or it's moving with a constant velocity. When a net force is not 0, okay, that's when an object is accelerating or decelerating. It's moving in some direction or changing its motion in some direction. So here's an object with a mass m. The forces acting on it are in the y direction, the weight down, Fg, and the normal force up, Fn. You'll notice we start keeping track over here, just like we did with projectile motion, with a xy chart. We do that because primarily gravity is only going to act in the y. Applied forces, when we push something to the left or to the right, are going to act in the x direction. So if it's not moving up or down, we say that the sum of the forces in the y is 0, so the weight is equal to the opposite of the normal. If we apply a force to the right, in this case, on a frictionless surface where there's nothing resisting that force, we can say that that's the only force acting on it, and so that's also equal to the net force acting on the object, F sub net. Since A equals F net divided by m, the amount of acceleration is going to be particular to how much applied force and how much mass the object has. Whee! Okay, so let's do an example problem. Here's a man pushing a 50 kilogram crate horizontally across a frictionless surface with a constant force of 100 newtons. Let's draw a free body diagram to start, not to be confused with fire-breathing dragons. Okay, there's our free body diagram. The crate has the weight acting down, the normal acting up, and the applied force, in this case, F sub A, to the right. What's the weight on the crate? Well, we can calculate it. Weight is simply Fg, which is equal to mg, 50 kilograms times negative 9.81 meters per second squared, gives you a weight of negative 490.5 newtons. Note it's negative because it's towards the Earth. Okay, what would the normal force be? Well, in this particular case, the normal force is just going to be the inverse of the weight, or positive 490.5, such that the sum of the forces in the y is equal to 0. Unless it's sinking into the ground or floating up off the Earth, usually those two forces are balanced. So what's the net force acting on this crate? Well, it's an applied force to the right, and you could say that since it's 100 newtons and it's acting horizontally, we could calculate the crate's acceleration using Newton's second law. F net over m equals a. 100 newtons divided by 50 kilograms, this crate will accelerate to the right at 2 meters per second squared. And from there we can do all kinds of kinematic stuff with this problem. Let's try another problem. In this particular problem, we have a horse pulling a 500 kilogram sled with a constant horizontal force of 3,000 newtons. The force of friction between the sled and the ground now is 500 newtons. So now we're going to start to deal with the force of friction. Friction is a force that always opposes the direction of motion. So we draw a free body diagram. Weight's acting down, normal's acting up. We'll say the horse is pulling to the right, therefore friction must be acting to the left. And there's all our forces drawn. What's the weight of the sled? Well, we know if it's 500 kilograms of mass, 500 times negative 9.81 meters per second squared gives us a weight of negative 4,905 newtons. The normal force, well, the ground will push back with a positive 4,905 newtons of force. What's the net force acting on this particular sled? Well, if the horse is pulling to the right with 3,000 newtons of force, but the frictional force is 500 newtons and it's the opposite direction, it has to be a negative sign, and therefore the net force acting on the object is 2,500 newtons. From there we can calculate the acceleration. Acceleration is 5 meters per second squared. I'll break this into another